The Peclet number is an important dimensionless number for problems involving advection and dispersion. And it's given here. The Peclet number is the characteristic length of the problem times the characteristic velocity divided by the dispersion. And it could be that it's hydrodynamic dispersion, but it could be that it's only diffusion. Sometimes you see the Peclet numbers defined that way. Okay, so to get a feel for what that means, let's take a look down here at important timescales in these transport problems. So the important timescale for the flow or for the advection process is given here. It's the characteristic length for the problem. This might be the characteristic length might be the size of the problem, or it might be the size of an important feature in the problem. And so it's that length divided by the velocity of the flow. So this has units of time, and you can think of this as the time that it would take for a particle to travel a distance L in a flow V. Okay, so it has pretty clear meaning. The time for diffusion is L squared divided by D, and you can work out the units that this has indeed units of time. Okay, so those are characteristic times. And then the way I think about it is that what we're really interested in is comparing the rate of advection to the rate of diffusion. So a rate has units of something over time. So the characteristic rate for advection will be 1 over this characteristic time, and the characteristic rate for diffusion will be 1 over this quantity here. Okay, so now to build the Peclet number, we're going to take the characteristic rate for advection divided by the characteristic rate for diffusion. And we do that here. So it's characteristic rate of advection, so that's the advection time is down here, and then the diffusion time is up here. And so we take the times that are defined here. The diffusion time is L squared over D. The advection time is L over V. We get a little bit of cancellation here of the L's, and we get that for the Peclet number. Okay, so what we think of when we see this now is that this is the characteristic rate of advection divided by the rate of diffusion or dispersion. And so if this number is a lot greater than 1, then it's mostly advection is happening in the problem, and if it's much less than 1, it's mostly diffusion. Now, as far as what process is most important, it really all depends on the details. We'll see an example of the spreading of a plume and how it's affected by advection and dispersion. In some cases, though, some processes are going to be limited by whichever one of these is the smallest. And so it could be that for problems where the Peclet number is large, that the rate limiting step is from diffusion. And where it's small, it could be that the thing that limits the overall rate is the advection. So it really depends on how the processes are arranged as to how you interpret the Peclet number. So let's go ahead and take a look at how it could be applied to a plume. So here's the Peclet number, and what we say for this problem, where we have a small source there, that's just, see that little circle right down there? That's a source of contaminants, and we just have one-dimensional flow. This is the same problem that we saw earlier. We have one-dimensional flow, and the water flows through the source and dissolves out some contaminants. And so the characteristic length for this problem is the diameter of the source. It's really the only length that we have here, the only fixed length, because the problem domain is this large, but I could have made it much larger and it wouldn't really have affected anything. So we use D for the characteristic length, and so the Peclet number then becomes this term here. Okay, so that's the first step. The next step that we have to see is that D, the hydrodynamic dispersion, that's approximately equal to the width of the plume squared divided by the the time that it takes to go from here to that point on the plume. Okay, so that's a way to think of the dispersion in a kind of an approximate way. And if we then substitute this D in there, then we get the Peclet number that's defined like this. And we can recognize that the velocity times the travel time is just simply the distance of the travel. And so there's delta L. And so we can simply substitute it in right there. And so this is another way to define the Peclet number, the diameter of the source and the distance downstream and the width of the plume. So this is kind of cool because now we're seeing that the Peclet number is defining the geometry of the plume, how wide it has spread in a certain distance. So what I did next is just rearrange this so that we have an expression for the width of the plume in terms of the Peclet number. So this is the width of the plume at some point delta L downstream. And we have some starting width here. And so we get a way to predict what the width of the plume is given the Peclet number. And now the Peclet number, it's given up here, well, right here, I guess. And so this is a number that we can determine up front. We can determine what the Peclet number is before we even solve the problem, because we know what the diameter of the source and the velocity and D is. So this gives us a way to anticipate what the width of the plume is as we move downstream. Okay, so that's one way to use the Peclet number in an actual analysis. Peclet number also comes up in numerical stability. And in this case, we define the Peclet number like this, where that characteristic length L becomes H, where H is the size of the individual finite elements. So the Peclet number will vary through the mesh if the mesh size varies and if the velocity varies. And what can happen then is that if the velocity is fast and the cell size is large, then this can be large compared to that. And what we find is that depending upon the kind of solver you use and how it's all set up, if the Peclet number is greater than 10 to 100, that can cause problems with the numerical stability. And so as you work out these transport problems, you will find, I think, in some cases that if you have a very fast velocity and a small amount of dispersion, that you'll run into problems where the concentration gets to be very large at a single point, and you have peculiar results that occur as a result of instability. One thing that you can do is look at the Peclet number. You can simply calculate this, and if you find regions where the Peclet number is large, then you could decrease it by either making H smaller, or making the mesh smaller, or you could increase D if there is a justification for that. Okay, so this is something that you probably will see as you work problems. COMSOL has a solver that is able to handle fairly large Peclet numbers, but you can't use it for all the problems. So if you run into difficulties with transport problems, then check out the Peclet number. If you do have problems and for whatever reason you can't decrease the mesh size, one reason would be that it makes the runtime very long, and there's no physical justification for increasing D, then what you might consider is using particle tracking instead of solving for the concentrations.